All right, having discussed scalar line integrals and vector line integrals, the last question, or the last topic, you might have been wondering about the question, well, what if we, instead of going from 0 to 2 pi in the last example, maybe what if we went the other way around? And so that gets at this idea of reparametrization. And so does the parametrization of the path matter? Okay. And so I just want you to pause right here, and I have the same image just copied. The only thing that's different is the direction of the path. And I want you to think about, and I forgot a symbol here, there should be a dot product in both of these. But I want you to pause the video and tell me if, in each case, if that vector line integral is going to be positive, negative, or 0. Okay, and so maybe you had some time to think. I believe the correct answers here should be that this is positive, and then this one is going to be negative. And the reason for this is if we think about the vector field, and this really represents, again, that's kind of the unit tangent vector, that's where it all came from. So what that's saying is that this is really the direction of motion. ds is really the direction of motion, and f is the direction of the vector field. So what this is saying is, and then you're thinking about that cosine of the angle in between because of the dot product. So if the cosine is, so relatively speaking, if the direction of both of these match, that means cosine is going to be 0, or at least very close to 0. The angle is going to be close to 0, so cosine is going to be 1, which is going to make it positive. And conversely, since these are in opposite directions, theta would be close to 180, which would make cosine negative, and so the whole thing is going to be negative. So the parametrization does matter. And so just the takeaway is that direction matters. Okay, and so just keep that in mind for a hot minute. We need to get through some definitions first. Well, there's this idea of simple. It's not, first of all, if you ever call a person simple, that's not a nice thing, so don't do that. But if you call a path simple, that just means that it's one-to-one. And so you might think, okay, it passes the horizontal line test. Roughly equivalent, but again, we're in multiple dimensions, so it's not exactly horizontal. And so the idea, I prefer to think of when we have more than one dimension, and we might think of that as a curve, we would say that it is simple if it is not self-intersecting. Okay, or that its parametrization is simple, so its path would be simple. Okay, so here I have a series of examples, and I just want you to pause the video here, indicate for each one if the curve is simple or if it's not simple. And then there was this idea of closed that we talked about so long ago, last semester, and I want you to tell me if the curve is either closed or not closed. So pause the video, take a shot of these. You should have 2 circles per line. Okay, and so the first one that is just this line segment that's a little swishy, this curve is going to be simple. It is not self-intersecting, so that is simple, and it is not closed. Closed would be that it has that its endpoint is where it started. Otherwise, the formal topological definition we'll get to in a little bit later. So here in the second one, this should be not simple and not closed. The next one is not simple, but it is closed. The next one is simple and closed. And this last one, believe it or not, is simple and it is closed. Okay, just some ideas as we move forward. Okay, now why do we care? Okay, the whole reason we care, and there's a lot of things going on here, so let me cover up some of this stuff. Okay, is because of this theorem. So if we have two different simple paths parametrizing the same curve, then let's see what each of them is saying. Okay, first of all, it's saying that in the first case that their scalar line integrals are the same. Okay, so as long as you have two simple C1 paths parameterizing the same curve, scalar line integrals are the same. As far as vector line integrals, if they go in the same direction, then their vector line integrals are going to be the same. If they go in opposite directions, then keep in mind that their vector line integrals are going to be opposite. Okay? And with that in mind, I want to go on to our last example here. So we have a vector field and the following parameterizations of the line segment between that. Okay, and so I'm curious about their vector line integrals, and I want you to pause before I give you the answer and tell me what you think. Okay, so if we're very careful, we can see, okay, well, these are all parameterizations of the same thing, right? Of the same curve. Okay, so I'm thinking it's too simple. Okay, yep, they're going to be simple because they're at most quadratic. They're not going to intersect themselves. Okay, fine. So I'm thinking that it's going to be one of these two cases. Okay, and so if I'm careful, I'm thinking, what is the direction that each one of these goes in? Okay, so for x, I'm going to say, okay, well, x would start at, when t is 0, right? So it would start at 1, 1, 1, if I put it in 0, and it would go to 1, 2, 4, okay, and similarly, y would go from 1, 1, 1, and go to 1, 2, 4. And lastly, z, and this is where we might have to be a little careful. When we start at -1, we actually start at 1 and then 2 and 4 and end up at 1, 1, 1. So z is going backwards by comparison. So even without calculating, I can tell you that the integral of the scalar line integral over x is going to be equal to the the vector line integral over y, but then this is going to be the negative, so the opposite sign of the vector line integral over z. Okay. All right, and so here I didn't ask for any calculations. This would be fine for an answer. If you want, I encourage you to do the calculation, and I will tell you that this ends up being 7, and then this ends up being 7, and then this ends up being negative of a -7. Okay, I did the calculation. Okay, just to make sure I did it right. So that's an important thing to consider. So as long as, if you do, you could have multiple parameterizations for a curve. Just know that if one traverses in the opposite direction of another, that you'll need to switch the signs. All right, and that's going to conclude this section on scalar and vector line integrals.